On the 17th of April 2025, in a video released by the University of Cambridge, a professor of astrophysics looked directly into the camera and used a word that scientists almost never allow themselves to use in public. Not exciting, not promising, not interesting. He called it profound. Niku Madhusudan, who had spent more than a decade of his career building toward this exact moment, said that humanity was watching new chemical processes unfold on a planet that could be habitable. And within hours, headlines across the world were carrying a claim that has haunted the human imagination since the first person looked up at the night sky and wondered if anyone was looking back. 124 light years from Earth, the James Webb Space Telescope had detected the chemical fingerprint of a molecule that, as far as anyone on this planet has ever been able to determine, is produced by exactly one process: life. This is the real story of K2-18b. Not the manufactured drama of a viral headline, but the actual, ongoing, deeply contested scientific event that has divided some of the most respected astronomers in the world, and that may, when the dust finally settles, represent the single most significant moment in the search for life beyond Earth since that search began. K2-18b orbits a small, cool, reddish star called a red dwarf, located 124 light-years from our solar system in the constellation Leo. It was first discovered by NASA's Kepler Space Telescope in 2015, identified through the subtle, repeating dimming of its star's light as the planet passed in front of it. A transit, the same basic technique astronomers have used to discover thousands of worlds beyond our solar system. K2-18b is what astronomers call a subneptune. Roughly 2.6 times the radius of Earth, larger than our home planet, but smaller than the ice giants of our own solar system, a category of world that does not exist anywhere among the 8 planets orbiting our Sun, and yet appears to be one of the most common types of planet in the entire galaxy. What made K2-18b a planet worth watching closely was its orbit. It completes a full circuit of its star in just 33 days, a blisteringly short year by Earth standards. But because its star is so much dimmer and cooler than our Sun, that tight orbit places the planet directly inside what astronomers call the habitable zone, the narrow band of distance from a star where temperatures could permit liquid water to exist on a planet's surface. Not too hot for water to boil away. Not too cold for it to freeze solid. The zone where, if conditions are right, oceans can exist. In 2019, and again in subsequent observations, astronomers detected water vapor in K2-18b's atmosphere, among the first such detections ever made for a planet sitting inside a habitable zone. That alone made it one of the most closely watched exoplanets in the sky. But it was the arrival of the James Webb Space Telescope, with its extraordinary sensitivity to infrared light and its ability to analyze the faint chemical signatures hidden in starlight filtering through a distant planet's atmosphere, that turned K2-18b from an interesting curiosity into the center of one of the most consequential scientific debates of the decade. To understand how a telescope sitting nearly 1 million miles from Earth, at the second Lagrange point where gravity allows a spacecraft to remain stable relative to both the Earth and Sun, can determine what gases exist in the atmosphere of a planet trillions of miles away, you need to understand the method astronomers call transmission spectroscopy. As K2-18b passes in front of its star from our point of view, a sliver of the star's light grazes through the upper atmosphere of the planet on its way to Webb's instruments. Different molecules in that atmosphere absorb light at very specific, very precise wavelengths, each gas leaving behind its own unique signature, the way a fingerprint identifies a specific individual. By measuring exactly which wavelengths of starlight are missing or dimmed as it passes through the planet's atmosphere, astronomers can determine with remarkable precision what that atmosphere is actually made of. Using this method, Madhusudan's team at Cambridge first reported in 2023 the detection of methane and carbon dioxide in K2-18b's atmosphere, a combination that, combined with the planet's position in the habitable zone and the earlier evidence of water vapor, led the team to propose an entirely new category of world. They called it a Hycean planet, a portmanteau of hydrogen and ocean, a theoretical type of exoplanet covered by a vast global ocean of liquid water, sealed beneath a thick, hydrogen-rich atmosphere. If such a world existed, and if its ocean retained liquid water at a habitable temperature beneath that hydrogen blanket, it would represent one of the most promising classes of planet in the search for life beyond our solar system. Potentially far more common across the galaxy than rocky, Earth-like worlds, and potentially far more accessible to detection given how clearly hydrogen-rich atmospheres show up in Webb's data. Buried within that 2023 data was something else, a faint, uncertain hint of a molecule called dimethyl sulfide, abbreviated DMS. On Earth, DMS is produced overwhelmingly by marine life. It is, quite literally, the chemical responsible for what is often described as the smell of the sea, released by phytoplankton, marine algae, and certain bacteria as part of their normal biological processes. As far as scientists have determined, on Earth, DMS production is almost entirely the work of living organisms. It is one of a small handful of molecules considered a legitimate astrobiological biosignature, a chemical fingerprint that, if found on another world in sufficient quantity, would be very difficult to explain through any process other than biology. The 2023 hint of DMS was too faint to mean anything on its own. The statistical confidence behind it was, in the language of astronomers, essentially indistinguishable from noise. But it was tantalizing enough that Madhusudan's team requested additional observation time on Webb, this time using a different instrument, the mid-infrared instrument known as MIRI, which observes a different and complementary range of wavelengths than the instrument used in the original 2023 study. The new data, gathered and analyzed over the following year and a half, arrived in April 2025, and this time the signal was not faint. Using their MIRI observations, Madhusudan's team reported detecting spectral features consistent with dimethyl sulfide and a closely related molecule called dimethyl disulfide, or DMDS, at what statisticians call 3 sigma confidence, meaning there was only roughly a 0.3% probability that what they were seeing was a random statistical fluke rather than a genuine signal in the data. 3 sigma is a meaningful threshold in science. It is not nothing. It is the level of confidence that has, in other fields of physics and astronomy, been treated as a legitimate basis for cautious, qualified announcement. But it falls short of 5 sigma, the gold standard that physicists require before they will describe a result as a confirmed discovery, the threshold that was required, for example, before scientists were willing to announce the detection of the Higgs boson in 2012. At 5 sigma, the probability of a chance fluke drops to roughly 1 in 3.5 million. At 3 sigma, there's still a meaningful chance, by the standards of rigorous science, that what looks like a signal is not one. Madhusudan's team was careful, in their formal published language, not to claim a confirmed discovery of life. NASA, breaking from its own pattern of celebratory press releases for previous Webb findings, declined to issue an official press release for the April 2025 announcement at all, a quiet but telling signal of how much internal disagreement and caution existed around the result even before outside scientists weighed in. The agency did release a statement reiterating, in careful and deliberately measured language, that confirming a true biosignature would require follow-up studies and multiple converging lines of evidence, and that any claim of this magnitude needed to rule out every plausible non-biological explanation before it could be taken as evidence of life. That caution proved well-founded, because almost immediately the wider astronomical community began pulling the result apart. What followed over the next year was exactly what good science is supposed to look like, even when it disappoints the part of us that wants a clean, thrilling answer. Independent researchers, working from the same publicly available Webb data, began running their own analyses, testing whether the statistical methods used in the original paper would hold up under different assumptions, different modeling techniques, and a wider range of possible alternative explanations. A team led by Jake Taylor published a research note applying a standard statistical test that astronomers have used in numerous previous studies, including studies that successfully detected water and carbon dioxide in other exoplanet atmospheres, and found that the supposed DMS detection did not pass that test with the same confidence the original team had reported. Madhusudan responded publicly, somewhat sharply, stating that nothing in the rebuttal worried him about the original result. Taylor, in turn, stood by his methodology, noting it had been a standard and respected first-look analysis in the field for years. Then, in August 2025, a more detailed and comprehensive reanalysis was published in the journal Astronomy and Astrophysics by an independent team that reprocessed the complete suite of Webb observations of K2-18b. Not just the MIRI data the original team had relied on, but the full combined data set across multiple instruments and multiple wavelength ranges. Their conclusion was sobering. They found that the strength of the apparent DMS and DMDS signal was highly sensitive to exactly how the raw data was processed and binned, meaning that small, seemingly reasonable choices in how scientists organized their data could swing the result dramatically, from appearing to be a real detection to appearing to be nothing at all. When they applied what they considered the most defensible data processing approach, the signal weakened substantially and was, by their assessment, no longer statistically significant. A separate paper, examining the question through a different and more rigorous statistical framework, specifically designed for evaluating claims of extraterrestrial life, reached an even more pointed conclusion. Reanalyzing the same public data with multiple independent reduction techniques, that team found that 87.5% of their analytical approaches did not support the presence of DMS or DMDS at all. Their formal conclusion stated plainly that what likely plagued the mid-infrared data was instrumental noise rather than a genuine signal from the planet's atmosphere, and that there was, as of their analysis, no statistically significant evidence for biosignatures in K2-18b's atmosphere. In response to the mounting disagreement, NASA itself took the unusual step of convening a collaborative, multi-team reanalysis, bringing together Renyu Hu at the Jet Propulsion Laboratory, Madhusudan's own group, and independent researchers, all working from the same combined dataset using a rigorous statistical approach called Bayesian analysis, specifically designed to let different teams test their assumptions against each other, rather than working in isolation. Hu explained the purpose plainly. Comparing results across multiple independent teams allows scientists to identify which conclusions are robust, regardless of modeling choices, and which conclusions are fragile, dependent on specific and debatable assumptions. The resulting study, posted in July 2025, confirmed that K2-18b does indeed have a complex, water-rich atmosphere, but found no conclusive evidence for DMS specifically. The biosignature claim, at least for now, could not be confirmed. This is the part of the story that a fabricated viral headline could never deliver, because it requires sitting with genuine uncertainty rather than manufacturing false closure. The scientific community working on K2-18b has not concluded that there is no life there. They have not concluded that there is. What they have collectively demonstrated, through an extraordinary and very public process of challenge, reanalysis, and counter-reanalysis, is that the question remains genuinely, rigorously open, and that getting it right matters more than getting an answer quickly. This caution is not new to the search for extraterrestrial life, and it is hard-earned. In 2020, a team of astronomers reported detecting phosphine gas in the atmosphere of Venus, another molecule considered a potential biosignature, since on Earth it is primarily associated with anaerobic microbial life. That announcement generated similar global excitement, similar dramatic headlines, and a similarly intense wave of scientific scrutiny that followed. Subsequent reanalyses found alternative explanations for the spectral features researchers had identified, and the original detection has remained deeply contested ever since. A quarter century earlier, in 1996, a team of NASA scientists announced that a meteorite originating from Mars contained what appeared to be fossilized evidence of ancient microbial life, structures resembling bacteria, preserved in rock that had traveled across interplanetary space. That claim, too, generated worldwide headlines and a presidential press conference. And that claim, too, was eventually undermined when researchers demonstrated that the key evidence, tiny magnetite crystals, once thought to be a biological signature, could be produced through entirely non-biological geological processes. The astronomers working on K2-18b know this history intimately. They are not eager to be the next chapter in it. As Madhusudan himself put it, even amid the controversy, the field is fortunate simply to be at a point where these conversations are possible at all, where a telescope sitting nearly 1 million miles from Earth can gather enough light from a planet 124 light-years away to argue in genuine scientific detail about whether that light carries the fingerprint of life. What makes this story extraordinary is not that scientists found definitive proof of alien life. They did not. What makes it extraordinary is what it represents about the current moment in the history of human knowledge. For the entirety of human civilization, the question of whether life exists beyond Earth was a question that could only be approached through philosophy, theology, and speculation. There was no instrument capable of testing it. No method existed for gathering actual physical evidence about conditions on a planet orbiting another star. That has changed within the lifetime of people watching this video, almost entirely because of one telescope. The James Webb Space Telescope, launched on Christmas Day in 2021 and now 4 years into its scientific mission, has fundamentally altered what kind of question "is there life elsewhere?" actually is. It is no longer purely philosophical. It is observational. It is testable, even if the test has not yet produced a conclusive answer. Webb has detected carbon dioxide in exoplanet atmospheres. It has detected sulfur dioxide, evidence of photochemistry occurring in real time on a distant world. It has mapped weather patterns on planets hundreds of light years away, identifying mineral clouds that form each morning and dissipate by evening, and atmospheres that show measurably different temperatures and chemistry between their dawn and dusk regions. It has peered into the atmosphere of a planet now famous for the most contested data point in modern astrobiology, and in doing so has demonstrated, beyond any reasonable dispute, that humanity now possesses the technical capability to ask these questions with real, falsifiable evidence. The honest answer about K2-18b, as of where the science currently stands, is this. There is a water-rich, chemically complex atmosphere around a planet sitting in its star's habitable zone, 124 light-years from where you are right now. There is an unresolved, contested, statistically uncertain signal that may or may not indicate the presence of a molecule that, on Earth, only living organisms produce. The scientific community is actively working to resolve that uncertainty, using some of the most sophisticated statistical and observational tools ever developed, in full public view, with every team's data, methods, and disagreements published openly for anyone to examine. That is not a manufactured shock headline. That is something rarer and, in its own way, more unimaginable than any fabricated claim could be. Humanity, for the first time in its existence, possessing an actual instrument capable of investigating whether we are alone in the universe, and having the patience, the rigor, and the intellectual honesty to keep checking the answer rather than simply declaring victory. Madhusudan called the moment profound. He may turn out to be right, or the signal that excited him may turn out to be noise, an artifact of instrument sensitivity and data processing choices. Another entry in the long and humbling history of biosignature, claims that did not survive scrutiny. Either way, something has already changed permanently. A telescope sitting nearly 1 million miles from Earth has looked at the faint light of a star 124 light-years away, passed that light through the atmosphere of a planet smaller than Neptune and larger than Earth, and extracted from it a question specific enough and serious enough that some of the finest scientific minds on this planet have spent more than a year arguing over what it means. Whatever the final answer turns out to be, the question itself, asked with real data, tested with real instruments, argued over with real scientific rigor, is the unimaginable thing, not a headline, not a claim. The simple, staggering fact that we can finally ask, and that somewhere out there, 124 light-years away, a planet sits quietly in the dark, holding the answer, waiting for us to look closely enough to be sure,